Thanks very much. So this is a talk called Lessons from the Demo Scene. Have anyone here actually heard of the demo scene? I'm aware of at least some people who haven't. Yeah? Okay, cool. This is good. So some of you will learn something, some of you will learn different things. So the content, I kind of normally do this same sort of way, just a sort of who, what, why kind of thing. So who am I? Why am I giving the talk? What is the demo scene for those people who don't know about it? And how can we as security professionals learn stuff from it? So my name is Pete Beck. I'm a Director of Services here, which is kind of a technical director role. Previously, I was a principal consultant at NCC. Then before that, BlackBerry, Microsoft, and some gov.uk things we don't talk about. More interestingly, I play the trumpet. I'm a former professional Lego builder. Disclaimer to start with, I'm showing a lot of screenshots in this presentation and a few animations. I do not claim credit for any of them except for this one. So they're all people who are much more talented than me. Who've been doing this for many years. I just put an Amiga ball in because... Sorry? Yeah, I totally agree. Yeah, I'm definitely an ST person, not an Amiga person, but I'm told that every presentation about the demo scene has to have an Amiga ball somewhere. It's kind of like a law. Okay, so why am I talking about this stuff? It's fairly obvious as soon as you scratch the surface that there are a number of similarities between people writing demos and people working in security. And that I think applies both to the skills involved and the mindset. I think it's also true that demos have kind of evolved as hardware's improved. So the picture on the left is from a demo called Stiletto from, I think it's about 2007. And the one on the right is by the same author from 2020 something. So the guy who did this worked at Pixar for a while. I think he worked on Brave and did The Grass, apparently, his claim to fame. But, demos have actually evolved to take advantage of improvements in hardware, both in terms of, how pretty stuff is, how fast it is, and so on. The desktop experience, on the other hand, hasn't really changed. We were sort of discussing this in the office. There isn't anything fundamentally different from like using Windows XP in about 2003 and using Windows 11 today in terms of the user experience. Yes, it's a bit prettier. Yes, there's lots of stuff going on behind the scenes you might not be aware of. But from a user's perspective, it's basically the same stuff. And also, it's a good excuse to kind of reminisce about some great demos and retro computers, which are things very close to my heart. I think I own 3 retro computers at this point. I've got a Beeb, an Electron, and an Atari ST. In our office, we have an Amiga. So, yeah. Okay, so what is the demo scene? And sort of how did it come about? A really nice way that somebody else came up with to think about demos is demos are to games as poetry is to prose. I think that's a really nice way. They just kind of exist for their own sake. So in the beginning, or at least back in the 1980s, software piracy was a big deal. People would typically buy games on cassettes, then try and remove the protection on those cassettes and put them onto floppy disks, which at the time were just about coming in and just about being affordable. But I can tell you the first 3.5-inch floppy I bought cost me £5.75 at a time when a pipe would have cost you about 50p. So discs were quite expensive. So what people would do is they'd crack the tape protection, put the tape onto disk, but then compress it to take less space, which means they needed fewer discs because discs were expensive. So for cracking it, there were lots of tools available. This is one from a Commodore 64 with lots of different tools designed to remove different types of protection. Then for packing, putting multiple games onto a disk to save space. This is from an Amiga. Again, this all predates things like PKZip and gzip and so on by quite a few years. So people were sort of rolling their own compression routines. As you start to put more games on a disk, what people start to do is add a menu. So you didn't have to like look what was on the disk and run a program. You just get a nice menu. So here's a very minimalist example of that kind of thing. But what happened is people thought, well, that's a bit boring, so let's make it a bit more interesting. And they started adding colors, animations, scroll texts, all sorts of stuff, just to make it a bit more interesting. And then they started adding credits and greetings. Now, this is like a really significant step. Just kind of greeting your mates might seem unimportant, but in a demo world, this is like getting your paper cited in an academic journal. So this is how you kind of gain kudos and reputation in the community. It's all about the greets, fundamentally. So as people added all these greetings, it became a very competitive thing to see who could do the best thing, because that would get you greets from other people who were inspired by your work and so on. It wasn't long before people realized that the actual crack games weren't as interesting as the intros people were putting on them. So we got started to get people just doing the intro thing without bothering to do any games. Initially, they were pretty simple. So typically just a single effect. Some early ones that people would do slideshows to show how good they were at doing graphics. Typically again with a scroll text, maybe some music. Another fairly common format was this sort of jukebox one where you get a whole bunch of different music tracks that you could listen to. Again, with some flashy scroll text and so on. But they very soon evolved. This is quite a recent demo, but you've got multiple parts that play one after the other. You've got, different effects like a plasma. You've got some very detailed images. You've got 3D effects of different types, some transparent, some shaded, some wireframe, and so on. So it's illustrating a lot of different kind of techniques. Some are interactive. This is actually the menu for one demo. So the idea is you fly this little spaceship around, land on a pad, and that's what chooses the next demo you see. But again, the credits and greetings were a big part of this. Now, demos were predominantly written by groups of people rather than individuals. Mostly in Northern Europe, I have to say, so Scandinavia, Germany, Poland, and the UK. And it started getting very competitive. Everyone was trying to do a better demo than their peers. To the point where we have these parties. This is one called Assembly, and I think this is 2005. So people would rock up with their computers at these massive parties, try to code the demo. There'd be competitions for different categories, like the best 4K demo, the best 64K demo, the best Amiga demo, the best boot sector demo, and so on. Lots of different categories. And people would have competitions. They'd be shown on the big screen, all very competitive. Now, so let's think about the skills these people have. Well, they're obviously writing very flashy effects on legacy hardware, typically is where they come from. So they'd be coding in assembly language. The fact that a lot of these are size limited means they're doing a lot of hand optimization. If you think about the origins and the cracking scene, removing protection from tapes or disks, you've got to have reverse engineering skills or debugging skills or both, because you'd be reading the code, trying to figure out how it worked, what the protection was. Some of them were very much based on runtime stuff. So people would use things like high resolution timers. So if you change the code or introduce any debugging, it would change the values in the timers, and the crypto key to decrypt the next section would be wrong. So you've also got a lot of low-level hardware knowledge, whether that's disk controllers, timing chips, that sort of thing. And you've got data compression. As I said, a lot of this packing stuff was before any of the main kind of compressors that we all know and love today really existed. And think about the mindset of these people as well. If you're writing these effects, the first thing you're going to do is cheat. A lot of the effects people have look really impressive until you realize there's no animation. They're just doing color cycling and setting the palette cleverly to give the impression of animation. So you cheat, you break the rules. They've got creative thinking, apart from obviously the design of these things, the way they approach certain tasks like trying to optimize code, trying to write faster code, smaller code, that actually requires a fairly creative approach to coding. It's not just doing stuff out of a textbook. And they're quite competitive. Now, in the security world, those are all things that will stand you in very good stead. both the skills and the mindset. We not necessarily competitive among each other, but we're always looking for bugs that other people have missed, right? We're always trying to find the bug in the website or the bug in the code. We're always trying to find the exploit. That's a very competitive mindset because you're trying to show you're smarter than the guy who wrote the code fundamentally. So now we've established there's quite a big overlap, certainly between people doing like native exploitation, reverse engineering, and demo sceners. How can we actually learn from this? So I've kind of come up with 5 lessons, sort of. I'm just going to go through those. So the first one is that teams work. So if we look at a demo crew, this is a group called The Exceptions, who sort of morphed into Thalian Software back in the late 1980s. Typically, there were about 3 to 6 members in a group. So if you look at a demo in the credits, you'll probably see about somewhere between 3 and 6 people who contributed. And they'd really specialize in different areas. So typically, one person would do coding, one person would do graphics, and one person would do music. And that's very clearly defined roles within that. Everyone could probably do some of everything, but people certainly had their own specialisms and areas of expertise. Think about security teams, though. When we're doing a gig, even a fairly large one, we probably only have 2 to 4 people. And we're covering all these different and fairly diverse specialisms, everything from threat modeling, design review, code review. We might be doing some reverse engineering. We might be doing static analysis, dynamic analysis, fuzzing. All of these skills are fundamentally fairly independent. We're also working across a whole bunch of different domains, network testing, web, mobile, cloud, embedded, IoT, ICS, whatever. There's lots and lots of different domains in which we apply those skills. So I guess the lesson here is security is a huge space, and it's completely fine not to know everything. Don't even expect people who've been doing it for 20 odd years to know everything. But it's really good to be an expert at something and have your own niche and your own area of expertise, and then try and find other experts to complement your skills and work with them. We find when we're doing sort of large system type tests for clients, so we might be looking at a doorbell. So you've got the physical doorbell that goes on your house. You've probably got a mobile application so you can see who's ringing your doorbell. And there's a ton of back-end infrastructure that make it work. We would typically have 3 people looking at each of those things. But even within that, we'd be looking at different types of testing. So for the doorbell, somebody might be playing with it, sticking probes on chips kind of thing. The other person might be reviewing the code to see if they could break the secure boot. So again, lots of different skills and applications. We're not expecting the guy who's reviewing the boot code to be able to test the web API at the back end, even if they could actually do that. We would regard those skills as independent. So work as a team and don't worry about trying to learn everything. The next lesson really is that assumptions are fairly bad. I mean, again, we know this as security professionals, but in the demo world, the classic thing is it can't be done. People say, you can't do that, it's impossible, you can't get that effect to work on this hardware. Probably the best example, or at least the most obvious one, is a technique called breaking the borders, which was on the Atari ST. So on the low-res screen of an Atari, you have 320 by 200 resolution, and you have 16 colors. So although this is a medium-res screen, you can see there's the white border that goes all the way around. By design, that border is always there. It's impossible to extend the screen to the edges. So obviously people come along and they do demos with lots more colors than 16. And they also do lots more pixels. So they go from a 320 by 200 screen to a 416 by 272. Now, the way they do this is frankly obscene. What they did was read the data sheet for the video controller chip. And they realized it was kind of a state machine. So what happens is, as the electron beam is going down the screen, at certain points, at certain numbers of cycles, they check things like the refresh rate. Because at certain cycles, what you want to do essentially is, when you get to this point, fire a horizontal blanking interrupt, which causes the electron beam to go back to the other side. What they did was, by changing the frequency of the screen at exactly the right point, they fooled the state machine into continuing to read more pixels because it wasn't quite the right set of conditions. So it might be, if the cycle number is this and we're at 60 hertz, fire a horizontal blank. If the cycle number is this and we're 50 hertz, fire a horizontal blank. By changing those frequencies at exactly the right points, you get to do some crazy stuff with the video controller. But that is, an amazing task of understanding low-level hardware, reverse engineering stuff, and very precisely timed software to actually leverage it to do something useful. In the security world, there's the kind of "it's not meant to do that" mantra that we get from clients all the time when we show them a vulnerability. So, for example, a lot of the time people make what are on the face of it perfectly valid assumptions, but they should never code like that. So we have a routine here that assumes that no one's got a password longer than 128 characters, so allows precisely 128 characters for a password, and does a strict copy into it. I'd love to tell you I made this up. The words HP Protect Tools might come to mind, just saying. That's quite old, but that really was the code. Again, people writing client-server software often assume that only the legitimate client will ever talk to the server and vice versa. So in this case, they're saying, well, we know the client only sends up to 4K because we wrote it. Therefore, we can assume that the data fits in a 4K buffer. They don't allow for the fact that a malicious user might write their own client. Similar sorts of things we get with integers. If anyone's ever looked at code that manipulates images, everywhere, I guarantee you will find an allocation of width times height somewhere. Every single image parser does this. Every single one I've ever looked at. Obviously, you get an integer overflow, which leads to an allocation that's too small, which is then exploitable, typically. But that's really common. A slightly more subtle one. There are actually, in these 2 lines of code, 2 examples of undefined behavior. Bonus points if anyone can spot them. Well, the idea is you can pass a negative number in, but if it's negative, it essentially takes its absolute value. What, sorry? Yeah. So there's one particular value that is minint, actually. So the largest negative integer will still be negative when you flip its sign because of the asymmetry that 2's complement has. And similarly, the next line, adding 1 to a signed integer. So signed integer overflow is technically undefined behavior in the C standard. And in practice, it always kind of does what you expect it to do, but it's technically undefined behavior. So again, that's an assumption that people make, that adding 1 to a number is always going to result in a number that's 1 bigger than the one you started with. A final sort of thing related to assumptions is use precise language. Say what you mean and mean what you say. So a really good example of this is a quote from Terry Pratchett where Death's talking to Morton says, "I don't know about you, but I could murder a curry." So there's a very interesting interview with Terry Pratchett where he's talking about translating this book into German. I said, you cannot translate that phrase into German. It just doesn't work. It kind of comes across exactly as, I could commit homicide on a spicy Indian dish. It's meaningless. But, I've just been talking about assumptions. If you heard someone say, I could murder a curry, it's probably not lunchtime, right? Beer is probably involved. It's probably a group of you, not an individual. You're all making those assumptions based on kind of social norms out of a 4-word, 5-word phrase that has nothing about the time of day, but you're all thinking you've got the same image in your head when someone says, I could murder a curry. And I think the same happens with code. When you see code, you often see what you expect to see based on previous experience and what usually happens around that. And by introducing those assumptions, you're potentially missing bugs. So the lessons, really take the time to figure out how stuff really works, not how you think it works or how people tell you it's meant to work. Always think adversarially. So assume that anything anyone tells you is at best a simplification, if not just completely wrong. Find those edge cases, with the negative numbers. That actually, there was a CVE in, I think it was Chrome in the JavaScript JIT compiler, where it assumed that the absolute value function was always returning a positive number, and then actually removed a check that there wasn't a negative number in the next step because it thought it was dead code, optimized it out. And that led to an out of bounds array index, which was an exploitable condition and allowed remote code execution fundamentally. And use precise language. So a good example of that would be someone might say to you, this code has a buffer overflow. That's really sloppy language. No one writes buffer overflows in their code. What you really want to say is, this code has a bug that might lead to a buffer overflow, or even better, this code has an unchecked write, which might cause memory corruption. That's precise language telling you what the problem is and what the consequences of that problem are. Just saying it's got a buffer overflow is mixing the kind of cause of the problem and its impact. Okay, so next one, size matters. So in demo coding, there's a category called size coding, where the idea is to write something that's really impressive in as small amount of code as possible. So this effect here is by a guy called Matthew Henry, and is 256 bytes of JavaScript. And it's quite a nice sort of raycast 3D thing. But you can do other stuff. This one is 1K, and it's just written in raw WASM. What people tend to do is obviously write optimized code, but they also use a technique called regpack, where you essentially replace variable names with single characters, you concatenate statements together, you essentially squeeze the code. But this is a 1K one. This is another one. This is 1K using JavaScript and WebGL. The actual code itself is a 1K and uses PNG compression to essentially get gzip for free. But if you look at the raw, commented, readable code, it's about 8K. So it's not particularly huge then. For reference, if you look at NVIDIA's reference code to implement the same algorithm, it's about 2.5 megs of C. Whereas this is 8K. It's quite staggering how much code people write to do simple effects. So yeah, we can look at a pretty demo for a while. So this is a screenshot from a demo called 19595 by a group called Plastic. It's about 20 megabytes. It's very impressive. I strongly advise you to go and look at the YouTube video of this one. I would stream it, but the internet here is rubbish. It weighs in 20 megs, not huge. A group called RGBA came along and did the same thing in under 64K. Don't infer anything by the quality of the screenshot. It looks identical. The music's pretty much the same. The video is the same. It's scarily good. And that is well worth watching just to see how much it can be compressed. And that's not just using code compression, that's optimization, procedural generation of textures, lots of very clever techniques for modeling shapes. On the Amiga back in early 90s, maybe, Andromeda did a version of a demo called Nexus 7. Again, look at the video. It's much more impressive than this one screenshot. That pretty much filled an 800K floppy disk. A few years back, a group called Loonies did the same on a PC in 8K. 2 orders of magnitude smaller. And again, it's not quite identical, but it's 95% identical in 1% of the code. Why am I telling you about this? Let's think about secure coding. I would say, as someone who's been in the industry a long time, secure coding is definitely improving. The quality of software today is massively better than it was 20 years ago. We've got better processes like SDLC and its variants. We've got better tooling. It's a very flashy static analysis and dynamic analysis tools. And we've got better education for developers. So all of these are making code more secure, reducing the number of bugs, without a doubt. But if we look at the number of CVEs by year, it's getting more. 2024 is lower only because I took this dump in August, and we've still got several months of the year left. So, yeah, if code's getting more secure, how come we're getting more bugs? Well, let's have a look at Chrome, since that's a good source of bugs for some people. This is the size of the installer for Chrome for different versions. So you can see from version 1, it's gone from 7 megs up to about 100 megs now. And that's the installer, not the size on your disk. Code is growing. This is the fundamental problem. It's growing at a faster rate than the quality is improving. So there are more CVEs. And that's a big problem for us, because as long as the growth in code outstrips the improvements in quality, there'll always be more bugs than there were last year. Why is it growing? Well, if you think about modern applications, we've got either managed languages or scripting languages typically. We've got these massive frameworks that people use like Electron or React or whatever. And people are using lots and lots of third-party libraries because they contain code that does kind of what they need. That leads to lots of problems. First one is dependency hell. I mean, every web app we do will report outdated dependencies, every single one without fail. There's a couple of problems here. First is that just keeping up to date with the latest version of every dependency and every dependency of that and every dependency of that is an absolute nightmare. It's almost an impossible task. Secondly, there's this huge potential for supply chain attacks for backdoors. So, if you've got a dependency that's importing a few others and a few others, the scope for that supply chain somewhere to have a vulnerable version in is massive, just because you're pulling in so much code from so many different sources. So that's a real issue. And this graph, it really is a dependency graph. It's not just a thing I made up. The other problem, of course, is code bloat. People are importing huge libraries, like Boost, for instance, for some really simple function, which they could have implemented in 10 lines of code. And they're importing a 10 or 100 meg library to do it. What that's doing is in itself adding more attack surface, because you're importing a whole bunch of code you're not using and statically linking it. That's adding a load of functionality you don't need, but might in itself make exploitation easier. So, at a very simple level, if you have to write a ROP chain, the more code you've got, the more gadgets are available. So adding all these potentially unwanted functions is a bad thing. Same with web apps. There's a very good chance that if you're trying to exploit some bug, if you've got loads of dependencies with lots and lots of different features in them that you may not be using, there may well be functions that call exactly what you need to exploit that bug. We also get just multiple layers of wrappers around really simple code. I remember looking at some code once and there were 6 layers deep just to do a memcopy. There wasn't any additional functionality. It was literally memcopy wrapped 6 times. So, of course, this affects both size and performance. So the lesson, sorry to say it, but I don't think modern applications are fundamentally securable. There's just too much code. Think about Chrome. I don't believe anyone could read the code for Chrome in their lifetime, let alone understand it and secure it. What we're doing at the moment is kind of a best efforts approach to finding obvious stuff and running a bunch of tools and trying to find stuff that's easy to find. Getting assurance there are no bugs in software is pretty much impossible for any modern application. But what the demo scene has told us is that code can be, in many cases, reduced by several orders of magnitude in size and still be functionally equivalent. So there's no reason for these, 100 megabyte installers. Slack is what, 150 megabytes download? It's a chat program. I type stuff, you see it. That's a few tens of kilobytes, right? Why do we need 150 megs to implement a chat program? I honestly have a real problem with that. So, what we need to be doing is pushing back to our clients and the developers saying, why are you doing this? you're making it impossible to secure your code. Okay, a related issue about timing. Timing is everything. So there's this concept called cycle accurate code. When I was talking about the Atari ST screen earlier, I mentioned having to flip the frequency at exactly the right point. What that relies on is very precisely timed code where you're running an exact number of instructions that take an exact number of cycles and then doing something. So the idea is that you can synchronize the code, the instructions in your code, and other things that are going on in hardware in the machine, typically video or audio. So there's this technique called racing the beam. This is a screenshot from an Atari 2600, which famously used it a lot. So the idea is that, like, an Atari 2600 did not have a display in the sense of it did not have a bitmap image that it displayed. It literally changed the color of pixels as the electron beam was moving across the screen. It didn't store any image. This technique's now been refined and used a lot. So the thing with the racing the beam is you basically wait for the beam to reach the end of a line and then change the color so the next line is rendered in a different color. Dead simple, but it's got to be done obviously at exactly the right moment. So you get this nice kind of rainbow effect. If it's done at the wrong time, you might get the color changing in the middle of the screen somewhere, and that's not what you want. So it's got to be very precise. It's very intolerant to any variation in those timings. Yeah, so this is H blank, horizontal blank. So it's the horizontal blanks when the beam goes from the right back to the left, and the V blanks when it goes from the bottom to the top. People have taken this thing to a whole new level. There's a thing called 0-bit plain demos. So this is an Atari ST demo. That image is actually moving in the real demo. I strongly advise to look at the video, and it isn't a bitmap. It's a single color on the screen, which is being changed at exactly the right point to do this effect. There's even 3D stuff. It's absolutely, even when you know how it works, understanding how someone could write code to do that, it's like magic tricks where knowing how the trick works, and it's still just as impressive, if not more impressive. So what these guys are doing is literally, you've got a background color here that's kind of a light yellow. It waits for so many cycles, then changes to black for one instruction, then changes it to a slightly darker yellow for a few instructions, and so on. That's how it's working, but it's done so precisely timed that you get this regular effect. And as I say, these things are very intolerant of any variation in timing. If the timing's not exact, you'll notice. There's a similar one with sampled sound. Why is it doing that? With sampled sound, obviously, if you're playing audio, as simulating the D2A converter by manually changing the volume of the sound you're playing to simulate a waveform, any variation in timing is going to cause clicks or something. Your ears are incredibly sensitive to those sorts of things and can pick it up, whether the pitch is going up or down, if there's clicks because stuff's not quite accurate and there are gaps. So this became quite a big deal. So people playing samples on systems where there was no D2A converter, essentially. And again, it had to be super accurate. So let's think about timing attacks that we've heard of. There are two main types of timing attacks that we see in modern systems. There are side channel attacks and race conditions. So a side channel attack is basically where you measure the time it takes for certain things to happen and use that to infer some data on the system. The two big examples of this, I think back in about 2017, they were discovered were Meltdown and Spectre. So this is where you could use effectively side effects of memory being cached to infer what a certain value in memory was, because the cached value would be much quicker to read than all of the uncached values. I strongly advise you to go and read up on this if you're interested. But essentially, you just do an operation with every possible byte value, and you expect one byte to be quicker because that's a value that's been cached, and that's the value that must have been in a memory location that caused it to be cached. Again, requires very precise timing, and the fix for this was fundamentally to remove high-resolution timer access from JavaScript in a lot of cases. And there have been other mitigations as well, but one of the first was to stop JavaScript being so accurate for timing. The other one, of course, is race conditions. That's typically where you've got multi-threaded code where at least one component's not thread safe. And typically what happens is you'll have some code which is calling some function, and then that's calling some other function. At some point, the code isn't thread safe. That typically happens on Linux systems with things like signal handlers, which need to be re-entrant but aren't always. And a recent example, there was a bug in SSH called regression. Again, CV from earlier this year. And that was basically a race condition in some logging code. Another Terry Pratchett quote is that essentially 1,000,000 to 1 chances can happen 9 times out of 10. And that's one of the ways I like to think about race conditions. Not that they're easy to exploit necessarily, or you've got a high probability of winning a race, more that you've just got unlimited goes, and computers are very fast at doing this kind of thing. So if you do have a 1 in a million chance of winning a race condition, try 10 million times. You've got statistically a very good chance that one of those will win it. So the lesson really from our demo scene is that although exploits can require precise timing, that is totally achievable. We've seen demos where precise timing is essential and people are actually showing off how precise it can be and doing some really crazy stuff. The other thing is that we tend to have unlimited attempts to win race conditions. And if it's a remote exploit, as FX once famously said in a talk, it's not my CPU. So you just thrash someone else's CPU until you win the race condition. Okay. Final one really is, I think old school computers are awesome. And I think they're a resource that people in security should actually get to know more. So think about a retro system. Memory is typically going from a few tens of kilobytes up to maybe 1 megabyte. So you are very much resource constrained in the amount of memory you've got. You've got a relatively slow CPU of the order of, say, 2 to about 8 megahertz, rather than several gigahertz, which we have these days. But you do have direct access to hardware in that you can program hardware using the registers on the devices themselves. Retro demos are still actively developed. There are some competitions which focus on particular systems. So Summer Hack here focuses on the Atari range of computers. There's some which focus on Amigas, Commodores, PCs, Spectrums, whatever. And you can see people are still writing demos for like Acorn Electron, BBC Micro, Spectrums, Amstrad CPC, Commodore 64, Atari ST, Amiga, and a PC with DOS. So it's a 16-bit PC demos. These are all active things that people are still developing on. Modern hardware, on the other hand, is a little bit different. Most of the time, the CPU is way faster than anybody actually needs, right? We're probably the exception, and we might sometimes hit it, but for most people, they will never hit 100% CPU utilization, even for an instant. It just isn't required. And you can code essentially like you've got unlimited memory and unlimited storage, right? I mean, how many people ever assume an allocation can fail these days? It's pretty rare. What that means is there's fundamentally no need to code efficiently. You don't need to write decent code. You've got this massive layer of abstraction as well between the hardware and the applications. It's done for very good reasons, so that it's a consistent interface if you want to play a sound, and it doesn't matter what hardware is actually generating that sound. But on the other hand, it makes it very difficult to understand how the hardware really works and what you can do with it. Yeah, more or less, completely. And the other thing I don't really like is this kind of planned obsolescence. Is where your computer, it doesn't meet the requirements because you've only got an i7 CPU. God, I mean, who has an i7 these days? I mean, wow, that's ridiculous, right? If that PC a few years ago, like 10 years ago, would have been a dream. And now we're told, it's not good enough because we're writing such crappy code that we need hardware to keep developing faster and faster just so we don't have to learn to code efficiently anymore. It's shocking. But all is not lost. Now, retro systems might be great to play with, but obviously, I'm not suggesting everyone goes onto eBay and buys an Amiga. Luckily, emulation is fantastic these days. You can get into retro hardware without having to buy anything. You can just download emulators, many of which are 100% cycle accurate and will do all of the tricks that the demo coders use, and that they support all of these quirks of the original hardware to allow people to run and, well, to write and run the old demos. So you can actually, really understand how stuff's working. There's even some really good development environments. So plugins for Visual Studio Code here for BBC Micro emulator and Amiga emulators. And you can write your code in VS Code. When you hit run, it spins up the emulator and runs it for you. Absolutely fantastic. The bar to entry now is so low to get onto these systems. One of the big problems back in the day is the development tools were fairly basic and the debugging tools are more or less non-existent. Now you've got emulators, and within the emulator, you often have a debugger. So you can look at memory, you can set breakpoints, you can single step code. It's absolute, compared to what it was, it's an absolute dream. So the lesson here is, if you want to learn low-level skills and understand how hardware really works, retro systems are a fantastic thing. They're also a great learning platform if you want to learn about things like low-level assembly optimization, constrained coding within an environment where you need to write fast code. And they're absolutely brilliant. And emulation makes it so easy to get into it all. So hopefully I've shown that security and demo scenes overlap hugely. Both showcase low-level skills and a creative mindset. And I think as security professionals, we can learn a lot from seeing how the demo scene has approached certain problems. Any questions?